something like that. So, two problems are open. Aziz, man, no. Okay. Material, body. Like for solving this problem, do you really care what resolution is?
What?
Like for solving this problem,
Doesn't matter.
doesn't matter, right?
Yeah. Got it.
But yeah, you can look in your notes. It's one of the biomaterials. I think it will be in your week 5 notes, biomaterials. Who has studied their notes so far? You should know what resilient is then.
I haven't studied these ones.
Resilience.
I only just started today.
Skin or bone? I'm trying to remember. One or the other.
Okay, keep reading, it will come up in this, I think. Resilient is able to store this much energy per square foot. So this is much more than the energy per unit volume that can be stored by compressing or stretching a steel column. Wow. Assume the steel is loaded to the yield point and is linearly elastic to this point.
I don't understand that.
What didn't you understand? What did you understand this?
I don't understand it at all.
This problem?
Oh, yeah, I didn't start reading it.
Okay. Okay, you can read for us. Like, let's read like, loudly. You can read. Dude, come on! Like this is the hard part in your exam. Like if you don't understand the problem, how will you solve it? See, resilient is able to store this much energy per cubic meter. So basically, what you have energy per unit volume. So energy per unit volume is given to you 2 into 10 power 6 joule. Okay. So that this is much more than the energy per unit volume that can be stored by compressing or stretching a steel column having yield stress and elastic modulus. So you have now scenarios you have steel bar. So basically in this problem you are trying to compare your biomaterial with like a metal. So you have sigma y given to you 425 megapascals. E is given to you 400. Assume the steel is linearly elastic to this point. Okay. So, again, you remember, like at least it is yield point, so you can assume, okay, linearly elastic follows Hooke's law. So sigma is just E epsilon. Okay. What is the formula which you need for this problem? So energy per unit volume. Formula we know is half sigma epsilon, right? That's it for energy per unit volume. Now, from here you know what is epsilon, so sigma over E, so sigma square divided by E. So this will be for your steel. Calculate from here, compare with that, and see it's much more.
Would an equation like that be given to us like
This?
Yeah.
Okay.
Right. Well, I'm gonna write it right now, but like still.
Cheat sheet. What do you want to cheat sheet?
Before this, I did not know about the equation.
Seriously?
Yeah.
V is volume.
Yeah, like energy per unit volume, it's also called like U. Like you remember, right? Like energy per, I've told you about this in my discussion also. Like energy per unit volume is half stress, strain. Don't you not familiar with this?
No.
Oh my
Oh my god. I haven't heard anything about it. I just need to know it.
Like the engine.
This is not grad part.
Which leads me to my next question. The next question is, it starts talking about a steel spring in the middle. It's not clear whether this steel spring is the beam or it's in addition to the beam.
What is the steel spring?
What steel spring?
What spring is that?
There's no spring mentioned anywhere else in the question.
Yeah, it's not, so it's okay. What if the steel spring is in the form of a beam loaded as a cantilever with a point?
I think the resonant is supposed to be the spring, maybe.
Wait a minute. Whether the beam
This is the kind of
no, it's
question
okay.
here that people have.
If a free wing has dual resonance springs. Okay, so if you know about resonance, it's assumed that you know it's like acts like a spring. First thing. Second, we were comparing resonance with steel. So now we'll compare steel spring and resonance springs. So that's what it is like. If you read the whole thing, it will make sense right here. Steel spring, resonance spring. And we have already compared resonance with steel. Yep. That's what it is.
Okay.
You can read the whole thing first and then start solving. Maybe it will make more sense.
Is the load on the cantilever intended to be normal to the beam? It's not clear. It just says there's a point load.
Uh-huh. What is this? Is in the form of a beam loaded as a with a point load at its end. Assume the beam width. See, it says like steel spring is in the form of a beam.
Well, if it's loaded as a cantilever, isn't it like
Yeah,
bending the
side,
beam?
side, yeah. Is in the form of beam and loaded. Okay, so that's again like you know what is your Have you written this down? Maybe? Solutions are there on this. So you don't have to think too much. You know this, cantilever, loaded switch. Right? Question. What is the question?
Nothing, just like for, in 2A for the solution, like it's just that last part that's shown.
Which one? Last part? The solution?
Yeah, and the solution is just your answer. You didn't say the formula or
Oh, yeah. Yeah, I was assuming like that is like universal known fact.
we know. That's that.
Okay. I think you can. Let me ask you, Professor. Like, can I give away these kinds of things? Like, if you say like I don't remember energy per unit volume, yeah, I'll have to give it to you. What else I can do? I'll ask you. But yeah, you have your cheat sheet. Put all your stuff from statics dynamics, like the very, very small things. Like this is what you know: stress, you know strain. What is next thing? What, energy.
Okay. Then this part B,
Mm-hmm.
it doesn't ask us to find anything. It says, what if the steel spring is in the form of a beam?
I
It just
think,
leaves it there.
It's a continuation, dude. Seriously.
yeah, it's just really bad English. He's just saying.
Bad English. I'll talk to this, like the writer of this book. This is from a book. So show that this is much more than the energy per unit volume. First, like the case 1. What is given to you in the beginning of the problem? Just energy per unit volume of your resonance. That's all it is given.
Mhm.
So it is now comparing that energy in different scenarios. First scenario is just by compressing the steel uniaxially. Second, compressing not compressing, loading the steel in a cantilever bending fashion. Now third is flea weighing has dual resonance swing containing a length. How high would it jump? So that energy, whatever you have, will transmit to your like potential energy change. So how high jump? Whenever height comes, what do you gain? Potential energy. What did you start with? Some energy in your resonance. So that energy converted into potential. Whenever height is there, you can think potential energy is involved. Yes, please.
Can you keep going on the cantilever beam part?
Yeah, I'm going to. I'm just giving him an overview of what is there. Okay, so make sense? If you read the whole problem, You started with an energy compared with steel uniaxially, then compared with steel in a cantilever manner, and then third, okay, forget about steel. I have an actual insect, flea. Okay. So, okay, first let me finish the cantilever part. Okay, one second.